Good evening. I'm afraid I've got to begin with some rather unfortunate news. As you may know, last July, the Russians launched 2 space probes to the neighborhood of the planet Mars, mainly to study not Mars itself, but Phobos, which is a chunk of rock less than 30 miles across. Well, sadly, one of those probes has now ceased to function. What apparently happened was that a faulty command was sent out, the computer didn't override it, and the probe simply went dead. Well, it's too early to be definite, but I'm afraid the chances of regaining contact with Phobos 1 are now pretty slim, so we've lost it, I'm afraid. And now we depend entirely upon Phobos 2, which luckily contains almost all the experiments also carried on Phobos 1. And Phobos 2 will get there next January, so let's hope there are no hitches there. But this, in fact, is a good time to talk about Mars, because the planet is exceptionally well placed. And here's a drawing I made of it a few nights ago with my own 15-inch reflector. And I may say that's the best view of Mars I've had for a long time. You can see there the southern polar ice cap, and south at the top in this drawing. You can see the dark areas, which are not old seas or seabeds. They're simply areas where the red, dusty stuff has been scoured away. And you can see the red areas that are known, quite reasonably, I think, as deserts. And that does show you the kind of view you can get now of Mars with a reasonable telescope. But of course, we don't see Mars well every year. When a planet is opposite to the sun in the sky, we say it is at opposition. And with Mars, that happens only every other year, and I'll show you why. Here we have the sun, and the Earth, and Mars, and they're almost lined up, so Mars is at opposition. That was 1986. Now, a year later, the Earth had been right round the sun and had completed one orbit. But Mars is traveling more slowly in a larger orbit, and it hadn't had time to get round. So in 1987, Mars was not well placed. The Earth had to catch Mars up, so to speak, and it only does so this month, when Mars is again at opposition. And as you can see from that diagram, Mars is then almost as close to us as it can ever get, less than 40 million miles away. And astronomically, that's not very far. So this is a very good time to observe Mars. And that's also why it is so brilliant. Look for it below the square of Pegasus, actually in Pisces, the fishes, and it's now brighter than any other star or planet apart from Venus. It's even brighter than Jupiter, which rises over to the east rather later at the night. So Mars really now is splendidly placed. But it's still nearly 40 million miles away, and that is a handicap. But we do, of course, have pictures direct from the Martian surface. And they were taken by the Viking probes of the 1970s. And Vikings 1 and 2 each dropped a lander down onto the Martian surface and sent back pictures showing a reddish, rock-strewn landscape under a pinkish sky, and there you can actually see part of the spacecraft. Mars is a fascinating place. It's also a paradise for geologists. And that's why I'm exceptionally glad to welcome back now one of our old friends, Dr. Peter Cattermole, who is a planetary geologist. Welcome back, Peter.
Thank you, Patrick.
Now, what is the surface of Mars really like?
Well, the first thing I think to note is that that warm red colour we see in all the pictures is very, very deceptive. In fact, Mars is a vast cold desert where the temperatures can fall as low as minus 143 degrees Celsius. Now, the second thing is the Viking probes and the Mariner 9 pictures have shown us that the Mars surface is different in different places, which is what we might expect. What we have found is that the 2 hemispheres of Mars are very different. And the southern 2/3 of the planet, seen in this diagram at the bottom of the picture, because I'm a geologist and I put everything the right way up, is very heavily cratered. And you can see the craters there. Impact craters these are. The northern part of the planet is much smoother. And what I've done here is to put on the contour, the zero contour, the kind of sea level of Mars. Mars has no seas, of course, but we have to have a reference horizon. And I've coloured in yellow the ground which is below the zero level. And most of the northern hemisphere is. And in the right-hand diagram particularly, you'll see the zero contour more or less follows that boundary, or the line of dichotomy between the cratered southern hemisphere and the smoother north. Now, if we put a little bit of geology on the maps, and I've now coloured the southern hemisphere in blue, and left the northern smoother hemisphere uncoloured, you will see that there is a discrepancy between the line of the zero contour. We can now superimpose these 2 pictures. We can now see a discrepancy between that zero contour and the cratered hemisphere. And this is a line of a huge bulge, which is called the Tharsis bulge. And on the left-hand hemisphere, the left-hand picture, you'll see a number of large red splodges, as it were, and these are enormous shield volcanoes, the Tharsis volcanoes. And this is one of the major topographic features of the planet. And like most volcanoes, these have associated with them lava flows and calderas, and here we see part of what's called Elysium Mons, and this is situated on one of the smaller bulges called the Elysium Bulge.
Peter, why are the two hemispheres so different, and how do the Martian volcanoes develop like this?
Well, early on in solar system history, there was a lot of loose dust and fragmental material around, and this peppered the old surfaces of the rocky planets, forming very heavily cratered surfaces. So we believe the cratered hemisphere of Mars is very old, perhaps 4,000 million years old or more, rather like the old surface of the Moon. And something must have happened to part of Mars' surface more recently, and somehow, perhaps by some kind of heat overturn inside Mars, the northern part of the planet was totally resurfaced and covered in volcanic materials. And so we have this dichotomy between the two hemispheres. And when that resurfacing of the northern hemisphere took place, there was a lot of volcanic activity, and we had the volcanic plains of the northern hemisphere. And gradually, with time, the volcanicity became focused in certain places, and we had these Tharsis shield volcanoes. And on this beautiful image process mosaic from the Flagstaff facility, we see the three Tharsis Montes on the left of the picture. Each a giant volcano, 25 kilometers high and about 550 kilometers across, and they sit astride the crest of this enormous bulge.
They produce many lava flows.
They produce many lava flows and other features which we're familiar with from the Earth. And this is a large lava flow perhaps 8 or 10 times longer than the sort of flows we get associated with Hawaii. And these flows flow down the flanks of the bulge. Because it was a bulge, it stretched the Martian crust, and we see thousands and thousands of fractures, cracks in the Martian crust, seen in this beautiful Viking image, which are very un-Earth-like. We don't see this kind of thing on the Earth.
You know, quite apart from the giant volcanoes, I always feel that the most spectacular feature of the entire Martian surface is the system of canyons that we call the Valles Marineris, or Mariner Valley.
Oh yes, Mariner Valley is one of the wonders of the solar system. Mariner Valley, of course, because it was discovered by Mariner 9. This is in fact a Viking mosaic, the same mosaic we showed before, and you can see this valley running along the Martian equator. It's roughly 4,000 kilometers long, which is the distance it would take to drive between Dublin and Cairo. And each of the big canyons is about 200 kilometers across and up to 7 kilometers deep. And it's a vast series of canyons which splays out from the eastern edge of the Tharsis Bulge.
Well, when you talk about canyons, one normally associates that with water activity, but I don't think that was cut by water, do you?
No, I think there's very little evidence that that kind of canyon is cut by water. It's far too straight and linear. All we've really found on the canyon floor is the movement of wind, and it seems that some kind of fracturing opened the canyons so that their floors slumped downwards, and the material from within has probably been moved slowly by gravity and by wind over millions and millions of years.
All the same, there is plenty of evidence for past water activity on Mars.
Oh, there's an enormous amount of activity. It's one of the other exciting things, particularly which the Viking pictures have showed us. And indeed there are river valleys of all persuasions. Now this is one of the more spectacular valleys, a lovely colour picture by Viking showing Mangala Vallis, which by the way is one of the possible sites for an American landing mission.
Yes, indeed.
And you see the floor of this big channel in the bottom of the picture. It's fairly smooth in this picture, and you can see a number of deep tributaries coming in from the north. Now when you focus down under high resolution on the floors of such channels, you often see these enormous scour marks, which can only really have been formed by the dragging and scouring along of fragments, boulders and the like, on the floor of the channel by a fast-flowing fluid, presumably water. Sometimes those fluids obviously encountered obstacles like an impact crater or a resistant rock, and you get the formation of a teardrop-shaped island left in the middle of the channel. These features really, I think, can only be put down to water. But they're not the only kinds of channels you get, and if you look at synoptic, broad, sort of brush images of Mars, you see channel networks which have well-defined tributaries, which could be mistaken quite easily for a terrestrial river system. These are in Lunae Planum, the centre of the Mars disk, and you can see beautiful tributary networks as the channels have flown from the left, the west to the east.
It's instructive too, isn't it, to plot the distribution of the channels?
Well, yes. The sort of channels we've talked about are not the only ones. Even in the cratered hemisphere, the cratered highlands, the ancient crust, we see lots of small channels in between the craters, and they're shown on this computerized map. You see it in the bottom of the pictures, lots of short yellow lines, and these are all tiny little channels. The major channels, the ones we've shown pictures of, are much longer. They're shown in light blue, And most of those channels are concentrated and flow towards the dichotomy, the line separating the upland hemisphere from the smoother one to the north.
Well, there's certainly been plenty of water on Mars in the past, and what about the flash floods, Peter?
Well, yes, these are most extraordinary things. These are called outflow channels. We don't really have much like it on Earth, not on this scale. This is one called Juventus Chasmi, and you'll see it's an enormous swath cut into the Martian desert. It's about 200 kilometres across, and it's several hundred kilometres long. In the left, it's just a jumble of blocks in a subsided block of the Martian crust, and you can see on the right, it's a whole series of enormous scour marks. No tributaries, it just starts and goes on. And we think these things form by enormous floods where water was very rapidly, perhaps almost instantaneously released by perhaps the melting of ice by volcanic outbreaks.
Well, people are going to say, what's happened to all the water? There isn't any liquid water on Mars now, and there can't be.
Well, no, there can't be. Mars's atmospheric pressure is too low, it's too cold. The only place the water can have gone, and it didn't escape into space, we believe, is beneath the Martian surface, into what we call the regolith and the subsoil. And it's presumably locked there as ice in the pores of the subsurface rocks.
Well, you can see a certain amount of ice at the poles, and I've got 3 drawings here which show how the polar caps of Mars change with the season. They're all made with the same telescope. This one was done in June with my 15-inch reflector. Mars is not quite round there, as you can see. It's showing a slight phase, it's slightly gibbous, and there is the southern cap, which is very large. Then warmer weather comes to Mars. This is a drawing made with the same telescope in August. And here's a drawing made in September, and the cap is now very much smaller, as you can see. And in Martian midsummer, the cap's going to become so small that I'll probably lose it. So, Peter, the wax and wane of the polar caps is important in all Martian study.
Well, yes. What you've shown there are the seasonal caps, the caps which grow at the appropriate winter for whichever pole we're talking about. And in fact, the melting and the release of volatiles into the atmosphere as those poles wax and wane is very important for the weather because it releases liquid into the atmosphere. Now, the 2 poles are rather different. The northern pole melts when the atmosphere of Mars is very clear. Therefore, a lot of sun's radiation can get through, and the carbon dioxide coating, which is what the caps are made of, and which we see here draping a scarp in the polar regions, this can completely melt, and it reveals that that north cap has a permanent cap of water ice beneath. The southern cap actually melts when there are dust storms around. And for that reason, the atmosphere is rather opaque, not so much that the solar heat can get through, and the carbon dioxide coating never completely melts, so we're not really sure whether there is water ice there or not. But both caps are very similar in another way, and this was revealed by certain quite spectacular Viking pictures, because around the poles, when the ice melts, you see a series of canyons and valleys in which there are laminated deposits, and you see some of these laminations towards the right of the picture there, where you can see some light red and almost grey to black markings. And these are 100-metre or so thick bands in which we think are locked up volcanic dust and volatiles, which were formed when the climate of Mars was very different from how it is today.
So Mars is a very strange world indeed. Peter, in some ways it's not too unlike the Earth. Would you like to try and summarise the similarities and the differences?
Yes, well, I'll try. Obviously, Mars and the Earth have certain similarities. We have volcanoes, we have canyons, river courses, and so on. But there are 2 major differences. First of all, the internal processes which gave rise to the volcanicity on Mars, and indeed the expulsion of water to cut the channels, seems to be of the very distant past. Now, of course, this is not the case on the Earth. Today, the Earth is very active, and we have volcanoes and, of course, rivers. So there's a difference of timing. The other thing is to do, I think, probably with the size of Mars. Size was very much smaller, couldn't retain an atmosphere, and it lost its internal heat much more quickly. So the activity was of the past. Now, the scale of things is also very different. The volcanoes on Mars are enormous. And if we were to compare the volcanoes of Tharsis, for instance, shown here in red, the Tharsis Montes and Olympus Mons, put those on a map of Europe, you'd see what enormous areas we're talking about for these vast volcanoes. A Hawaiian volcano would be quite lost in that particular map.
Of course, Olympus Mons is 3 times the height of Everest.
Olympus Mons is a real giant. It's slightly off the crest of the Tharsis Rise. It's about 27 kilometres high, and it has an enormous pit at the top of its 500 or so kilometre wide shield. And we have pits like this in Hawaii. They're called calderas, and you can visit one today if you go to Hawaii. On Mars, these things are enormous. Hawaii ones are just a few kilometres across. This one seen here, which has 3 components, as you see, the smaller component is over 40 kilometres across, so they're real giants.
And why are the Martian volcanoes so much larger and more massive than ours?
Well, this again has to do with how Mars works and how it's different from the Earth. Earth is very much larger, it's much more dynamic. Now, the Earth's crust, the outer part of the crust, is called the lithosphere, and this is in constant, very slow movement. And on this diagram here, you'll see the lithosphere shown in brown, a little bit of yellow beneath, and it moves very slowly at a few centimetres a year laterally. Now, the volcanoes, such as Hawaiian volcanoes, are built on the lithosphere by the movement of heat and magma from within. And that internal layer is known as the mantle. That does not move sideways, it moves upwards in a sort of convective motion. Gradually, the heat source for a typical Hawaiian volcano drifts away from the volcano itself, which is moved sideways on the lithosphere. So there is a maximum size to which an Earth volcano can grow. It's called plate tectonics, this process, and it doesn't seem to have started on Mars. It was too small. And on Mars it seems as though the heat source sat beneath the volcanoes for very, very long periods of time. And I mean long, the orders of thousands of millions of years. So they're very much bigger.
Do you think the Martian volcanoes are active now, or are they completely dead?
There's very little evidence they're active today. I think they probably died out perhaps 100 million years ago, or perhaps even more.
Well, let's come back now, shall we, for a moment, to the dust, because after all, Mars does have major dust storms, and sometimes the dust obscures the entire planet. And I've got two drawings here, both made by my own telescope again, which I think show this. One was made, actually, last night, and there is Mars with its polar cap and its surface features quite clearly seen. Now, in 1973, conditions were pretty similar. Mars was almost as close, quite well placed. I was using the same telescope under good conditions, and this is all I could see. Mars was completely covered by a layer of dust, and these dust storms do occur. I'd expected one before now, and it hasn't started yet as far as I can see. So they are important.
They're extremely important because once dust is raised into the Martian atmosphere, it renders the sun's rays opaque. And this has a fundamental effect on the Martian weather. And a lot of people are trying to study how the dust moves on the Martian surface, because this is one way of tracking down how the winds blow. So today, one of the most active processes on the planet is the movement of dust. But there is another process which is active, and that relates to how the cratered hemisphere, the southern hemisphere, and we can now come back to this map we showed earlier on, now showed in blue here, the southern crater's hemisphere. If you concentrate on that right-hand hemisphere, you'll see a grey region separating the northern from the southern hemisphere. And within this region, you see very peculiar channeled features. They're called fretted channels. And on the floors of these channels, you see the movement of dust-sized material with a kind of laminar flow. And you can see those lines on the floors of some of those channels where the material, which is actively been eroded from the cratered uplands, is moving inexorably and very slowly towards the lower ground of the northern hemisphere.
Well, the space probes have already told us a great deal. What do you think, Peter, is going to happen next? What's the future of space research with regard to Mars and its system?
Well, the thing I would like to see now are some of the photographs that have come back, we hope, from Phobos 2. Now, although the Phobos mission is really related to Mars' satellite, Phobos 2 is hoping to take some multispectral images of the planet Mars. And these are images taken in light of different wavelengths. And if we choose a correct wavelength, it can tell us something about the rocks. So from a remote source, we can learn something about the rocks. So I'd like to see those first. Now, I'm biased because I'm a geologist, but I would like to know more about the Martian rocks. And the obvious way to do that, barring a man, is to put a rover on the surface. And that rover could move around, sampling the surface. It could even send radar waves into the subsurface to see if there's ice or other rock types beneath.
This, of course, is an artist's impression, one of Paul Doherty's, sunrise upon Mars and a Martian rover sitting there on the actual surface of the planet and the Earth and the Moon shining down from the pink Martian sky. And that could quite easily happen within the next 10 years. I think it probably will. And we also may have a sample and return probe, and then, of course, we'll know definitely whether there ever has been any life on Mars. Peter, what's your guess?
I would say it's going to take a fair while, no life.
Well, we'll soon find out, I think. Meanwhile, things are going ahead. Phobos 2 is on its way, other probes are planned, and of course Mars is beautifully placed now. So don't forget to take the chance. Go and find it with the naked eye. Turn a telescope toward it if you can, because remember, it's now almost as close as it can ever get. And from Earth, you'll never see Mars better than you can do during the next few weeks. So from Peter and myself, good night.
There's another chance to see Mars in close-up, and that edition of The Sky at Night is a second showing at 6:30 on Saturday on BBC Two.